All right.
Dixon.
I think I got it. All right. So I have all the missions. All right. Thank you. Thank you. All right. Let me begin with a word of prayer. No. Dear Heavenly Father, we thank you for this day again. I thank you for these students. Just ask you to guide our steps today. Help us to prepare for the final test in here. Well, before the final. And just help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So here's the, whoa, who put that there? The solution to mission 3. So I guess we can look through here for a minute. I think you found problem 1 to be relaxing. Yeah? Yes. I like problem 1. So if you have a finite collection of masses, we just mass times position vector and then divide by the total mass. That gets us the center of mass, right? So there's that. Next up, oops. This one here was ambiguous until I told you it went 45 degrees above and below. I told you that at some point. Without that, there's like infinitely many answers. And yeah, I think there's infinitely many answers. I'm actually kind of on the bubble here. This may be...
I think that it can only be 45 degrees above and below.
Is that true? That's because I had the same mass above and below?
Right.
Yeah, I think that's what it is. Right. I must have been thinking of like an unequal mass problem when I was fussing more. I think when I did this problem last year, I just said, well, obviously the same velocity above and below, because otherwise you'd have vertical momentum afterwards. So VA has to be equal to VB and go from there. But anyway, the particulars of this problem aside, the general story here is in a collision, we want to conserve momentum before and after a collision or an explosion, some event of this nature. We can conserve momentum, and that forces us to have the vertical components to cancel out, and the horizontal components have to, together give us that horizontal momentum. And the reason we don't use 500 here, of course, as many of you have found out, is because we're at the top of the flight, right? So the velocity is decreased because gravity has slowed us down, right? However, gravity doesn't slow down the x component because of constant acceleration in the x direction. If you think about it, you've got the same mass going horizontally, right? Like you have the same horizontal momentum. So if you think about it, you could write the another way to understand what's going on here is this is something I haven't emphasized probably enough in here, but kinetic energy, right, is equal to P dot P divided by 2m. Or you could write that as the x momentum squared divided by twice the mass plus the y momentum squared divided by twice the mass. Yeah? So if you think about that formula, it's fairly obvious that we're increasing the kinetic energy after the explosion, right? Because the x momentum is the same before and after. So you've got that same kinetic energy in the x direction, but you've got additional y kinetic energy. So it makes sense that, I mean, obviously, like intuitively speaking, of course, an explosion releases kinetic energy, right? Anyway, so I worked out the algebra here, and we get 612.4 meters per second for the velocity. And the difference in the kinetic energy before and after the explosion works out to about 2,344 joules. Obviously, I'm not a practitioner of significant figures in here. Don't tell the chemists. As you know, they care infinitely more than I do about it. Let's see here. Problem 43 is the ballistic pendulum problem. And so it gets stuck to the pendulum bob in part A. So I conserve momentum, right? That tells me the velocity right before the upswing, v1, is given by this equation here. So like V1 is mv naught over m plus m. But then energy is conserved in the upswing, so we have the initial kinetic energy of the mass and bullet combination is equal to the final potential energy of the mass and bullet combination, because at the height of the upswing, the velocity is 0, right? So the energy is purely potential. So, so what I do is I solve the first equation for V naught, and then I think I plugged it in. No, I solved it for V. What'd I do? I solved for V. I rearranged the first equation like for V1, and then I took this V1 and plugged it in here, and this gave me the initial speed as a function of the height that it swings up to. Right, so there it is. Your formula might have looked a little bit different, but that's what it is. And then for the elastic case, because the impact is essentially one-dimensional, we can use the relative velocity theorem, which says that for an elastic collision, the difference in velocities before and after is minus each other, right? I spent like a half-hour class time working this out. Remember, it was somewhat painful. And anyway, after the dust settles, what we have here is that V naught is equal to minus VA plus VB, where I've defined VA to be the velocity of the bullet and VB to be the velocity of the pendulum bob. So this time the bullet bounces off the bob, basically. So now I've got the the consequence of the relative velocity theorem for an elastic collision, and I also have conservation of momentum. So what I did was I multiplied this equation by m to make them look the same, and then I added the equations, so I get 2mv naught. These guys cancel because I don't care about VA. I don't care about the velocity of the bullet, so get rid of it. And then big M plus little m times VB. So I can solve for V naught as a function of the velocity of the bob, the big mass. And then on the other hand, I have the kinetic energy of the pendulum bob is equal to the potential energy of it at the upswing. What happens to the bullet, we don't care. It bounces off, like we can't keep track of that. That whatever that energy does, it's irrelevant to the second, like the final upswing. And so we end up with actually 1/2. In this situation, you only need 1/2 of the velocity that we needed for part A. So this is the same formula, but with a half out front. So I thought that was kind of cool. Which kind of makes sense, right? Like, well, let me shut up, because I'm just going to start coughing. Any questions? All right, let's go on. This one here is the glancing elastic collision problem. I was trying hard to make this work with unequal masses, and it just ain't the case. Right, you have to have equal masses for this thing to work out. But if the masses are equal, it's super nice, because when you write down conservation of momentum, the masses are gone, you know? And then, so from the y, from the x equation, I have this. From the conservation of y momentum, I've got that. From conservation of kinetic energy, because it's assumed to be elastic, I have this. But I divide by half the mass, and I got, V naught squared is a squared plus b squared. So what I do is I square this equation and that equation and add them. And then something nice happens. Now, if you didn't do all this, if you just were like, well, this is an elastic glancing collision in 2 dimensions, and we proved in class that the angle between the, the products is 90 degrees, you could do that. That's fine. However, to be clear, if I was to ask this question on the test, I would like to see it derived. All right? So like the steps do matter to me. It's almost never the case on the test that I just want you to write down the answer. It's almost always the case that I'm looking for some kind of derivation. So if in doubt, ask me. I mean, on occasion I do ask like a little throwaway question. I'm just looking for the answer, but it's not usually that. Excuse me. So I squared the x component and the y component for momentum conservation. I added them. Cosine squared plus sine squared is 1. I use that twice. But on the other hand, I also have that v naught squared is equal to the sum of the VA squared and VB squared here from the conservation of kinetic energy. So then you can cancel, you get cosine, cosine minus sine, sine equal to 0, but you guys are well aware that that is cosine of alpha plus beta. So therefore, cosine of the sum of the angles is 0, which means the sum of the angles must be 90 degrees. So there's that. And then the other question's easier to answer. We know that VA squared plus VB squared is V naught squared, so I can solve for VA since I know V naught is 15 and I know VB is 10. Those are both given, right? So there you go. Any questions? Yeah.
How does the system gain kinetic energy with this? Because the pucks are equal out, right?
Mm-hmm.
But then the final velocities add up to more than the initial velocity of the puck.
But they're not going in the same direction. They're going at 90 degrees up, 90 degrees opposite. So like one has gained momentum upward, the other has gained momentum downward. But the sums of the squares of their velocities works out to, like if you take 10 squared, right? 10 squared plus 11, like 11 squared is 121, right? So 11 squared plus 10 squared is about like 221, but it's a little bit more because it's 0.18. But 15 squared is 225, so like the sums of the squares of the velocities before and after, it matches. Because the velocity of the puck at rest is 0. So that you can see from the numbers here that the kinetic energy is in fact conserved. It's not that, like in an elastic collision, it's not that the velocities add, it's the kinetic energy is conserved, right? So this one's stupidly easy compared to some other problems in this homework. So here we have constant angular acceleration. How embarrassing that I've asked you a question about this, right? So I talk to Dr. Budarez sometimes. He has utter disdain for constant acceleration problems. It's hilarious. Like he doesn't think this course is not worthy of them. You know, that's basically his opinion, which I find amusing. But I mean, I respect it. I mean, you know, it's true. Like, I don't know, is it true? Like, there's a fair number of things in life that are pretty much constant acceleration, you know, like this primarily being the example. But there's a lot of things like this, you know? Oops. Anyway, so these are the I'm using the constant acceleration formulas, right? So we can only use those if the angular acceleration is constant. I'm trying to say that so that you remember it. Because a quick way to lose like 90% of the credit on a problem is to use the constant acceleration formulas in a non-constant acceleration problem. It's worth very little to us here. Okay, so context matters. Anyway, so here are the initial angular, it was initially at rest, so we had omega naught 0. The angular acceleration is 2.3, we got 2 seconds. It's funny how the answers to A, B, and C all work out to 4.6, but for sort of different reasons and different units, obviously, right? So like the change in angle, omega naught t plus 1/2 alpha t squared, well, 0. And that's still 4.6, this time radians. I should have asked you to give your answer in terms of revolutions or something so you felt like it was different, you know? How would you give this answer in terms of revolutions if you wanted to? I heard a multiply by 2 pi. I've heard divide by 2 pi. I think we got to make a decision.
Factorial.
Factorial? What's wrong with you people? No, divide. We should divide. Definitely divide. Divide by 2 pi. The torque is equal to I alpha. So I is given to be 2.0 kilogram meters squared here. And so I multiply by 2.3 radians per second squared, I get 4.6 Newton meters. Remember, the radian doesn't survive. It's a funny thing, right? Like people say, well, the radians aren't real in this sense, you know? And they're not wrong. Like radians are dimensionless. Do you understand why that is? What is a radian? What formula tells you that radians are dimensionless? Like the fundamental formula is this: S is equal to r theta, right? So this has units of like, length. This is a length, right? So that means that theta is dimensionless, right? So why do we have radians? It's to remind us, remind your reader that you're using radian measure as opposed to another measure like, angles. Angles, listen to me. Degrees, maybe? Degrees, yeah. You guys ever heard of grads? It's on your calculator, you know what it is? I think if I remember right, there's 400 grads like all the way around. So instead of 90 degrees, it's like instead of 90 degrees, I think it's 100 grad. I don't know why would you do this, but I've heard about it. I've never seen it used anywhere. Now this one, the angular acceleration is not constant, right? It's not constant. It's t to the fourth minus 2. So there's two stages here. I'm trying to find the change in theta. So I first integrate to find the angular velocity as a function of time. So integrating acceleration gives me angular velocity. I integrated from time 1 to time t. This t bar is an integration variable, so that gives me omega of t minus omega of 1, and then 1/5 t bar to the 5th minus 2 t bar. Evaluate from 1 to t, plug it in, I get this, but omega 1 was given to be 30. And after I clean it up, come on, I get omega of t is 31.8 minus 2t plus 1/5 t to the 5th. And you can check this, right? If I plug in t equals to 1, what happens? I get 31.8 minus 2 plus what is, what's 1/5? 0.2, right? So minus 2 plus 0.2 is minus 1.8. So 31.8 minus 1.8 is 30. It checks, right? Omega of 1 is 30 as it's supposed to be. So, I mean, it's just something you guys got to be aware of, right? We have to fit initial conditions. We have to fit initial conditions carefully. And then to calculate the change in theta, I integrate d theta dt, which is omega. And so the change in theta is the integral of this, which works out to 30.9. Let's see here. And up next, the wagon wheel problem, I think is fun. So there's 6 spokes. Each spoke has 1/3 mr squared because it's round its end. The moment of inertia for the rim, 4 mr squared, because I told you the mass of the rim was 4m. So the total moment of inertia for the wheel altogether is 6 mr squared, and the total mass for the rim is 10 times m, right? Yeah. How what? I coughed. I didn't hear you.
What if we considered instead of 6 spokes as 3 spokes, but with twice the length, and then doing it around the center? How come the math doesn't work? Or like just right now, I was looking at it. It looks like it would claim to be like 1/4 mr squared for.
Well, are you saying that the mass of each spoke is 2m?
Oh,
Because it would have to be then. Because I said that the spokes are 6 spokes each of mass m. I do assume a spoke goes from the axle out to the rim. Like a spoke is not a diameter. If I'm wrong, I'm sorry. Do you guys think of a spoke as a diameter? Radii, okay. Cool. All right, so once we work out the moment of inertia, then it should be easy sailing, give or take. So we have the wagon wheel, it rolls down without slipping. V is equal to R omega is the rolling without slipping condition. And so the potential energy at the start is 10 mgh, because you've got 10 mass up there. And then it falls down, rolls down to here. And at that point, all of the energy is kinetic. There's 2 pieces, right? There's the translational kinetic energy and the rotational kinetic energy, which, after I do the math, I get to solve for VF, and I get that. So Excuse me. Try not to cough on you guys. You knew it when you sat there. You knew what you're getting into. So here's the Atwood machine with a massive pulley. I suppose there are various ways to do this. I was talking to one of you, and we were talking about how to do this with energy conservation. There is another way to do this with energy conservation. You could. But the trouble with the energy conservation is, I guess, the same trouble. Well, I don't know if it's the same trouble, but you could use conservation of energy here if you wanted to. I chose to go the dynamical route, solving Newton's equations and such. So I have, well, anyway, are there any questions about this? I think we've talked about this one in class before. So, like, different things going on here. This is the rotational Newton's law, right? I times alpha is the torque, the net torque. So you have RT1 going like here, and minus RT2 going like that. So I'm defining this direction as positive alpha, corresponding to A being positive. That's my choice. And so like M1A is M1G minus T1, and over here you've got M2A is equal to T2 going up minus M2G going down. So one of the things that will trip you up on here, and in my notes, in my posted handwritten notes, there's an error here. I have assumed that the acceleration 0 in my posted, I hope I made an announcement about this. If I didn't, I'm sorry, but it is corrected in the type notes. So like we do have to think of the tension here being different on the different sides because the pulley's massive now, so like the tension doesn't have to be the same on both sides. Anyway, I then add the equations, and then what? What I do next?
You replaced T1 minus T, or T2.
Oh, yeah, thank you. So you're saying I use this right here, I plugged it in here. Yeah, that is what I did. And then I solved for I, since that's what we're looking for. Anyway, so there's that one. Come on. This one's nice. Yo-yo's got 300 joules of energy in the form of rotational kinetic energy. Yo-yo also has an angular momentum of 20 meters squared kilogram per second. What's the moment of inertia of the yo-yo? So kinetic energy is 1/2 I omega squared. And I know the kinetic energy, and what else do I know? I know L, so I can solve for I, and there it is. Not much to say there. So here's the turntable problem. So the way to solve part A is to conserve angular momentum. Like before and after the bird lands, the angular momentum is conserved. So the angular momentum before I naught omega naught is equal to the final angular momentum. Now, so why is I naught 1/2 mr squared? It's because we're talking about a disk, right? A solid disk. And the moment of inertia about the center of the disk is 1/2 mr squared. We worked that out. And omega 1 is whatever it was given here. And then afterwards, you have the moment of inertia of the disk plus the moment of inertia of the parakeet, which is just mr squared, because I'm assuming that the parakeet lands at the edge of the record player there. So let's see here. That's how to answer part A. And then let's see, part B, becoming dizzy, the parakeet jumps off with a velocity relative to the turntable in the direction of its rotation. So in some sense that means that should mean it's going to slow it down, right? It's going to kind of push off of it in the direction, which means it's going to push the turntable back. So you kind of expect that the Oof. Well, yeah, I mean, it's omega 2 is smaller. So omega F, if you think about it, so here's omega F, here's omega 2 after the bird jumps off. It is smaller than this, right? Because this fraction is smaller than 1. You're taking a fraction smaller than 1 and multiplying the speed that we had just after the bird landed, right? So omega 2 is a lower velocity, that angular velocity. Anyway, so question?
So, is omega F supposed to equal omega 2? It looks like the same.
No, they're not equal.
They're not.
There's omega 1 here.
Because that's multiplying in the numerator. That would be M.
Are they equal? What was I just thinking? Oopsie. Oh no. Huh.
So if you get points detracted, do we all get points then?
Just a second. Let me
That was a joke, sorry.
try to get, you're fine. I try to get away from it. I'm sorry, I was just talking myself into this being a different,
I think it's because the initial angular momentum used M instead of M plus the mass of the period. It should be like
where,
M
is there a, so there's a mistake here?
Used
Where would you say the mistake is?
Used L.
Initial angular momentum should be 1/2 M plus M r squared.
Yeah, yeah. Huh.
Big M plus the 1. Because the initial condition is when the pair is still on the disk.
Yeah,
So it would be,
well, there's something wrong here anyway. Let me look at this, guys, and let me, there's obviously something wrong here. Give me a second here. So it's weird. Part B has nothing to do with the jump speed at all. You know? So like the solution to part B is nonsense. It's not, that's not right. Yeah, anyway, I'll work this back out, guys, and I'll post it later today, okay? Let's go on. So moving on here. Yeah, so let us agree that problem 50 is, as currently posted, is incorrect. So if you just mindlessly copied the solution from last year, sorry. You'd be wrong. Oops. Now here, this one's super annoying because it's like I've intentionally not given you the right angle to use in every single instance, you know? Almost like the whole point of this problem was trying to make you think through what angle you need to use to calculate torque. That actually was the point of this problem. That and to give you infinite suffering in finding the moment of inertia, of course. Well, not infinite suffering. It's we actually told you it, right? So whatever. But so here, the torque that comes from force 2, we'll start with that one. The radial arm, so the pivot point's here, right? So this is the radial direction. And so the angle is this. This is the angle we need in order to calculate the part of this force which is directly perpendicular to the radial arm. So this angle alpha 2 relative to theta 2 is what? It's theta 2 minus 90 gives me alpha 2. Over here, if you look at the radial direction on the point C, you know, extending out from the pivot point like that, you can see from geometry here that that's 45 degrees. Over here, for this point B down here at the force 1, this angle is related to theta 1. They're complementary, right? So like theta 90 degrees minus theta 1 should give me this, what I've called alpha 1 here, just to give them names. So I've got respectively 60, 70, and 45 degrees are the, come on, angles I need. And so I have, you know, force times distance times sine of the angle between the radial arm and the force in each case. And I get 121.02 Newton meters out of the page. And so then working through the moment of inertia, I worked out 53.33 kilogram meters squared. And so then torque is I alpha, so the alpha is 2.269 radians per second squared is what I got. So, and at least one of you got this, so we're either both right or both wrong. Anybody else get this? Okay, good, good. Some of you were like, is this supposed to be ugly? Well, yeah, it's ugly. It's like really ugly. And I have no regrets. It's good for your learning. You should suffer some ugly things. It is a little bit ugly. I mean, there's this. And I at this point, I bailed on this page. I was like, all right, fine. I don't have my pen is not small enough.
No way.
So, yeah. So, yeah, I got this. And then, I don't know, I messed with it just to, so there's the format I chose to simplify. It doesn't really simplify much, honestly. I had hope, but yeah, it's ugly. And then, C, I got this. And so like part B is torque, part C is angular momentum. Yeah, they're kind of ugly. True, it's true, it's all true. And then part D, I differentiate the part B and some stuff cancels, woohoo! And that is in fact matches what I have earlier, so yay, I can differentiate and take cross products. I hope you can too. And this is not surprising, of course, because the derivative of this cross that by the product rule is this, but this guy is just mv cross v, which is 0, so of course that just leaves us r cross m dv dt. The laziest way to do this part of the problem would be to have done it like this, ignoring my formulas, right? Because it's a general identity. But that is not what I intended, although I would have had to respect it if you did that. Now, is this a reasonable test question? Yes. Wow. Thank you. I'm proud of you. I'm very proud of you right now. Man, some of you have grown. This is amazing. I feel better. I feel so much better. Now, this is not a reasonable test question, not because it's too hard for you, but because it's too hard for me to grade. So, see, it's all about me. It's all about me, actually. No, if I was to ask this question, I would try to find a slightly simpler formula that would put you through the same motions, but perhaps with a more sparse, something where we at least had 0 in one of the components, and maybe just polynomials as opposed to sines and cosines. I don't know. There's a way to make this problem interesting, but the calculation much smaller, right? Like, how about I omit units and I just give you things like cosine of 2t rather than cosine of omega t, that kind of thing, you know? That could make it a little bit less annoying. Anyway, this one actually, as any of you who've come to talk to me have discovered, is actually really simple. So the force of gravity, we're assuming the sun is at the center of the orbital plane. By the way, you can prove that there's an orbital, the proof that there's an orbital plane is actually here. This is the proof that there's an orbital plane. See, because the angular momentum, if you think about angular momentum, what is it? Angular momentum L is r cross v, right? So if the angular momentum, ooh, that was bad. If the angular momentum is constant, that means that r and v are like, they're in the same plane, right? If you think about it. I mean, that's not quite a proof, but plausibility perhaps. And if r and v are in the same plane, that means that the motion is stuck in a plane. The motion's planar, right? So, I mean, why do the planets, you know, largely occupy the same plane of, you know, orbit? Why aren't the planets, why isn't there like one planet here and another one like doing this, another one like this? They're not like that. They're all in the same orbital plane, yeah? It's kind of a mystery, isn't it? Anyway, so So here, it's very simple. Like the force is minus GMM over R. And we can just, and this is the formula I was trying to sell you guys on the other day, right? Rather than R hat, R cubed down here, R up here, that's still like reciprocal inverse square law. It's just a nicer way to write the formula. And that just makes it obvious that when I take the torque, calculate the torque, which is R cross F, which is what I should do, right? Because we proved that dl dt is the torque. So if you want to show that the L is constant, you should look at the torque, because torque is dl dt. And you'd like to show dl dt is 0 to show it's conserved. And indeed, the torque is 0, because we end up with just R cross R, which of course is 0. And, and this is true whether or not the force is, it's true whether or not the, I mean, I've drawn it for more of an elliptical orbit up to the limits of my artistry, because it doesn't have to be circular. This is a general truth for what are called central forces. It actually doesn't even, this actually doesn't even depend. If you look at it, does it depend on the inverse square? It doesn't depend at all on the fact that this is an inverse square law. It would be enough for the force just to be directed on the line that connects the masses, right? That's called a central force, and angular momentum is conserved for central forces essentially by this calculation. So anyway, that's it for that one. This one here's pain, but once you understand what you're doing, it's not too bad. So you measure the gravitational acceleration at particular altitudes 2 meters per second. After hiking 10 kilometers vertically, you find the gravitational acceleration has dropped to 1 meters per second squared. Find the mass of the mystery planet and determine your initial distance from the center of the planet. So, I put us at the, I put us 2 meters per second squared at the surface of the planet. I mean, it could be that we're already on top of a mountain and then we hike further up. It doesn't really matter, you know. It doesn't really matter. If you invented another variable for like your initial position, that would somehow cancel out in the algebra. But I just make the initial position at the radius for the planet, and then you hike up to r plus h. You've got 2 meters per second squared on the surface. You've got 1 meter per second squared here. Acceleration due to gravity is gm divided by r plus h squared, right? Because the force is gmm over the distance from the center of the planet squared. So then, I just, come on, here we go. I do the math. So I've got, this is that, and so I solve for gm both places, which gives me a quadratic, which I solve, and I get that. And then, once I know that, I can go back and find out that the mass is a mere 1.747 times 10 to the 19th kilograms. So, it's a wee little planet, isn't it? No? Yes? No? What?
Why'd you put 10 to the 40?
It's r squared. It's 24.14 kilometers. That's a good question, actually. Didn't we? Yeah, didn't we just find that r was?
You have R in kilometers, so you turn it back into meters.
Well, yeah, but so you guys got the same answer, but you didn't. You don't. So what we're disagreeing with this right here, right? This is sketchy. Yeah.
You put in the change from the initial position to the final position there, not the planet's radius.
Uh-oh.
Scroll up. Or you would have put the change, except it's 10 times the change. You put in the height, which is 10 kilometers, which is 10 to the 40 meters. 10 to the third. 10 kilometers is 10 to the 40.
Yeah.
Oh, 10.
But that's not what should have.
Oh yeah. That should not. That's not what we want there. Let's see here.
Yeah. Square. Okay.
Yeah.
Well, I was just thinking that's awful tiny. Well, I guess again, you didn't realize it, but the posted solutions were a trap. Because this is wrong, right? So what should we do? We should actually put that here, right? Let's work it out. Goodness gracious. I guess I've got some things to fix before I go home.
I did calculate, I think I calculated it right. And I still got that.
Where'd this equation come? Oh, it came from there. Wait a minute. Yeah, but the R should be the 24 point. Okay, so 2 times 24140 squared, big number, divided by, let me see if I can do this right. Shift constant 39. Oh yeah. Oh, it's that. This is the number though. So that is not this. So this is, I don't know what this is, but you could just get rid of this. This is trash. That is actually, I just worked it out. I mean, I plugged this number into here, multiplied by 2, divided by that, I got this. So, sorry about that.
So you got 1.747 times 10 to the 19th.
Yeah.
That middle thing gives.
I got to the 13.
Okay, I did that too. I was getting like 10, 14 so if you
I don't know what to tell you. Like this, I mean, just to verify, this is 10 to the minus 11th downstairs, right?
Yeah.
And I've got, this is actually 2 times 10 to the what? 10 to the 4th. So, so you've got like a 2 times a 2 times a 2, roughly speaking. So the 2's and the 6, they kind of cancel out. Really, you're just left with like a 10 to the 8th over 10 to the minus 11th, which is 10 to the 19. This makes sense, magnitude-wise. All right, let's move on here. Sorry about that. Obviously typo. So I added some color to try to help us see it better. Let me zoom out a bit here. So this is not my best work here, but if you can here is it. So that just gives you this little loop. That's it. Because outside of that, you'd have negative kinetic energy, which is no bueno. And then up here, the blue, energy 3, it gives you this guy and that little loop right there-ish. And then up here, energy 2, it gives you this guy and that guy. And then energy 1, the motion's unbounded, so it gives you this one and that one. And again, this is not very good. This, well, it's like this, but anyway, when I ask these, I'm somewhat generous on my grading, but I do have some some standards. So, you know, try your best if I do ask one of these, but like some general features you should look for. Symmetry. Whatever happens up here, the identical thing has to happen down there. There's always this like mirroring of the diagram is one thing. All right? Yep.
Then in that diagram, down 2 from the axis instead of down 1?
Like I said, this is not my best work. Yes, yes. Like I said, this is not my best work. It should be symmetrical. Yes. This is not ideal. This should be like that. Very good. Yes, exactly what I was talking about. So if I was to give this answer on a test, I'd take off like 20%, something like that. I'm just joking. Only 30%. No, 10%. I should stop.
We can negotiate.
We can negotiate. Let's see here. A ninja, of course, why not? Concentrates his considerable power, throws his opponent vertically at a speed of 10 kilometers a second. Whoa. What's the maximum height the opponent reaches? Earth-based ninjas. So here's the formulas. Work it out. And I got that. So What is that?
A lot.
20, what was the Earth radius again? It was what? 10 to the 7th. So this is how many Earth radii this is? H is what, like?
It's like 3, isn't it? A little over 3.
Well, I don't know. Didn't we work it out in class for like 8 kilometers a second? I'm trying to remember what we did in class. 2.57. To add 2. Let's see here, 25.7. I'm just kind of curious about something. So that's like, this is an altitude. So this is an altitude of 4 Earth radii. So that means you're about 5 Earth radius away from the center of the Earth at this altitude. We worked out in class that if you had 8 kilometers a second, we got to about 2 Earth radii away from the center of the Earth. So our altitude was just 1 Earth radius, roughly speaking. So that makes sense. We're a little bit farther out because we had 10 kilometers a second as opposed to just 8 kilometers a second in class. It doesn't matter what the mass is, by the way, right? For the speed. Now, it does matter very much, right? It would take much more energy for me to, say, throw this, expo thing at 8 kilometers a second upward, as opposed to, say, this marker cap, right? It would take a lot less energy to throw this marker cap at 8 kilometers a second upward. Although I will say that I would need to work out my throwing arm considerably to reach either of these velocities, but I mean, it's of course impossible. Like, stop with your nonsense. Let's go on. The Lagrange point, it seems so simple. It seems so simple, but it's so unpleasant. So the Lagrange point is the place where the force of gravity on the moon and the force of gravity from the Earth balance out. There's a point between the Earth and the moon where you're truly weightless. Yeah? And it's a real pain to find out where that point is in terms of the algebra, because you're working out, that the sum of the distance is the distance from the Earth to the moon, and and you've got that the forces are balancing like that, but the algebra is just a pain. You're like, this wasn't in our homework. We don't have to talk about this, but it is a reasonable test question. Let's see here. So this one here is a nice problem. If I have a problem like this on the test, and I have wording like this, you probably should ask me, what on earth are you talking about? Is the rod like this? Is it like this? Because I didn't say. Now you guys figured it out because you're looking at the solution from last year, I get it. But which I told you to, that's fine. I am not complaining about that at all. Seriously. I'm just saying that I would be critical of my problem statement. It was not clear what the geometry was here, okay? So if you see something like that, say something on the test, yeah? Then there's this problem, hooray, and this one, and we worked this one in class essentially. What was the difference with the one in class is I had what? I had a mass at the center, right? So if you set that mass to 0, this is the answer, I believe. Anyway, have a good weekend, peoples. I will try to make an announcement once I fix the parakeet problem. Sorry if you lost points because of my errors.